Hey everyone, my name is Gjeta and this is James. When James first asked me to present with him in Berlin, I was thrilled. It was a chance for me to talk about the cool technology that I'm working on and to hear about other people's Scala projects, and obviously I was excited to see Berlin for the first time. But I was also a bit surprised. I joined the team only a year and a half ago as an engineer on the core technology that we're presenting today. And in that time, I've worked on some really exciting projects, but it is a daunting team to join fresh out of uni, and so I'd also spent a lot of time feeling incompetent and asking stupid questions. But anyway, since James was asking me to present with him, I figured I must be doing something right at last. But then James told me the topic of today's talk. And then I realized that actually maybe I was being punished. And that's because today we're going to talk about change. I know what you're thinking. Who comes to a Scala presentation to give a talk about change? A conference where functional is king and where the words mutable var are mildly uncomfortable at best and just insulting at worst. But don't worry, we're hoping that by the end of this talk, we'll have convinced you that the technology that we've built allows us to combine the benefits of immutable state without forcing the developer to give up the freedom to deal with change. Okay, it's probably about time I introduced our project. James and I are part of a team that's developed a platform on top of which developers across multiple business lines at the bank can write financial applications, from CPU-intensive risk calculation engines to reactive UIs and trader desktop applications. So our clients are first and foremost the developers themselves. And our overarching aim is to build our platform in such a way that developers get to write the code that they want to write and to control the runtime so that it ensures that this code runs in the way that they want it to run. In our last presentation, we spoke about this for the first time in London a few months ago, and we described the platform as a platform that could automatically parallelize user code. And by the way, that talk is online if you're interested, but you don't need to have watched it to understand the concepts in today's talk. So our focus last time was on parallelization, and we talked about trade-offs. Our developers give up the freedom to control their own multi-threading, but they gain back fast and efficient parallelization controlled by the platform instead. And today we're going to talk kind of a little bit more about trade-offs, because different programming paradigms force developers to deal with change in different ways. And what that means is that we're sometimes forced to kind of pay a price for dealing with change. So as I mentioned, I am an engineer on the project, and I work on the core technology. And that covers the compiler plugin, the scheduler, and the cache, among many other cool things. And I'll talk about all of those later. James has been involved in the project since it began about 6.5 years ago. And I'm not really sure what he does every day. But he's seen the project grow into one of the biggest Scala code bases in the world, with over 3 million lines of code and more than 20,000 pull requests into the main branch by something like 500 active developers worldwide. And of those lines of code, about 60,000 cover the platform itself, the core technology, and the rest is application code that's been built on top of that. And of those 500 developers, only about 50 work on the platform. So, as someone wise once said, I forget who, the only thing that's constant is change. And so as developers, we have to deal with change whether we like it or not. And the reality is that in any long-running application, in any real system that's live for more than like a few milliseconds, we're going to have to deal with state and mutable state. And that might come because of a number of different things, whether it's something as simple as time ticking forwards, or temperatures and prices fluctuating, or users updating their preferences. So our challenge, in order to satisfy the requirements of our clients, of the developers, is to build our platform so that developers can write the code that they want to write without losing the benefits of immutable state, and without incurring some of the costs involved. And that's what James is going to talk about next.
Good, thank you. Hi. So I'm going to use some pictures. I'm going to talk about the two paradigms of essentially not functional programming, OO, procedural programming, and functional programming. I'm going to talk a bit about change in those paradigms and why in both cases it's not fully satisfactory for us, before we talk about what we actually did to make ourselves happy. And so I come from an OO background, and before the advent of threads, life was relatively good. When the program ran, you could debug it quite easily. You could put in breakpoints. You could see the change that you were making. It was relatively easy to work out how you managed to get into a particular state. If you ran the program again, it will probably do the same thing because there's not multi-threading. Then multi-threading arrived, and stuff got a whole lot harder. And when you debug multi-threaded code, you kind of wind up in this situation where you're trying to comprehend what's happening in all these call stacks and the interaction that those call stacks are having with the heap, and to try and work out what it is and how you wind up with this end state. And anyone who's done this will recognize the pain. It's very hard to keep it in track. Then you also have the problem is, if you put a breakpoint in one of these threads and stop it, then it's like the once you observe the system, it changes its behavior. Because now either you stop the other threads at the same time, or you allow the other threads to continue, but because your thread isn't continuing, it's not making changes, and that it did make in the case where the bug had happened. And I'm sure that many people are familiar with this kind of pain of chasing some race condition bug where you run the thing 100 times and it reproduces twice. And then you stick in some log statements, and then that doesn't reproduce it because the log statements have changed the timing, so you can't find the problem. So in a procedural OO world, dealing with changes, and it's almost always the changes that are causing these bugs, because you've decided you've incremented something outside of a lock or something like this. Those are the things that actually cause you the pain when you're trying to debug these things, and it's the change that happens. On the flip side, syntactically and at the point of change, what you write is kind of quite nice, and it's very easy to understand what it is, the change that you're trying to introduce into the system. So while the procedural model might not be it might be the code you want to write, it's certainly not the code you want to debug, because it's very, very painful to debug. And so this hasn't proved satisfactory to us. I'm sure to some extent we're preaching to the converted, right? But dealing with change in a traditional manner has been very, very hard. However, then we move into the functional programming world, and I'm going to show some code. This code here consists of 3 classes. It's a very simple piece of code for hypothesized flight, and some things to calculate the fuel cost, for which you need an FX rate. These things contain each other in an ABC style chain, and we have we have code that's similar to this and more complicated, which we'll show later, in loads of our systems. But in the functional world, you don't have this problem of mutation, right? In pure functional programming, there's no change, right? You want to change something, so if we create this thing like this and we want to change the fuel cost from 8.88 to something else, then what we do is we copy the object chain, right? So we take that FX rate and we copy it, and then we copy the things that contain it, and then we copy the things that contain them, and so now we've created a chain of copied objects, and that's how we get that's how we get a new thing with a new value, and that's how we deal with change in most FP models. Now, it's not very nice to write and understand. There are a lot of helpers for this. So there are these things like lenses, which means that you can write that, and obviously it's about half as much. And it shows how you can write the same kind of thing, which does the same thing. It still creates the new objects, but it does it in a way which is easier to read. But it's still not that easy to read. It's still not this. right? And that's the change that you're trying to introduce, is you're trying to say, I want to change that thing there and I want to change it to 8.13, right? And that line at the top is not as easy to read as that. And it doesn't change the underlying mechanics. So the underlying mechanics are still the same as still creating all those objects, which we'll talk about shortly. But before we do that, I want to show a kind of an increasingly more real-world example. Now, as Gjeta said, like, we've got millions of lines of Scala code, so we can't show you that. But what we can show you is like a typical and more complex example. And this is a similar thing. We've got the flight, and the flight contains the fuel cost, and the fuel cost contains the FX rate. But there are also some other things like when airlines are pricing their flights, they want to do stuff concerned with occupancy, right? Because anybody who's got children, if you fly during school holidays, they charge you more. And they charge you more because they know that the occupancy is going to be higher, and they can push the price up, and they'll still sell all the seats, right? And so what you need to do in order to work your price out is you need some kind of relationship to occupancy. And in this model, we're hypothesizing that occupancy actually depends on FX rate, which isn't crazy. You know, when the exchange rate between the UK and the US changes, like, whole loads of shoppers from the UK get on airplanes and go to New York and go shopping. Like, that is a real thing that happens. So in this case, you wind up with something that's a bit more complex, but it's still not an insane thing for you to want to draw, right, as an object graph. And this collection of references is what starts to build the complexity. But it's kind of logical because you're trying to model the real world, right? Now, I've got a picture here. We don't have a graphics or art department, so my children drew this for copyright reasons. And here, the thing on the left there represents the flight, and the flight contains these two things. It contains the fuel cost and it contains the occupancy score. And both the fuel cost and the occupancy score, they reference that FX rate, which is the rightmost bottom circle, and the occupancy score also the fuel cost also references this local price thing, right? So now when I want to do something, like when I want to change the FX rate, which is the right bottom one of those things, if I'm going to be efficient, I only want to change those bottom-most 4 objects, right? I don't want to change the other one because it's not changing. So now I wind up with something that looks like this. You all keeping track? Right, we're done with that. You all do follow that? Was all good? No, it's complicated, right? Because you have to create this interim. Well, you don't have to, but it's better to create this interim variable. You have to read it. Now, what's happening is, as a programmer, you have to kind of track these object graphs. Now, it's true, I can contort my business model so that I wind up with directed graphs, so that the changes I make are only ever in the line. So I can use something like a lens to do that. But it's painful, right? Because now I start to model in a way which is actually dependent on how the code I'll later write. And also, it means I have to kind of know, a priori, the things I'm probably going to want to change. And that's hard too, because, you know, like, you just don't tend to know the end state of your system when you start building it, right? So that's another problem. And in the real world, this is more like what the object graphs look like. Like, they're much more complicated than the 5 objects that I showed on the previous page. And there's interrelation, and yes, people will say, well, we shouldn't have cycles. But realistically, in the real world, you wind up with cycles because it makes your code easier to write, and it models the real world more. So whilst there are tools to help manage this in the FP world, they're not intuitive. It's not simple. A simple thing to do, and change is just very hard to deal with. And they always still result in copying. So let's talk about copying. So copying stuff is not free, and I think everyone knows that. But just to labour the point, this is a snapshot from Profiler. So Rory made the snapshot for us. We've been doing some work on Scala performance, and this is a snapshot of like object creation inside of the compiler. It's from compiling Akka, which is about 30,000 lines of Scala, and when we do that compile, it creates like 73 million 73 million objects in the JVM. Now, the people who write the compiler, they're like very aware of how much it costs to do object creation. So actually there's mutation inside of the compiler, which makes it there to be less object creation. So I think, you know, if you just were to write this in a purely functional way, you could have even more object creation. And what we know is that on the JVM platform, when you have all this object creation, and you know, if you don't have people who are expert and they're able to stop that object creation so that you get more performance, you just wind up paying the price in the garbage collection cycles. So you know, the first thing we do when we're trying to like optimize our JVM platform is we'll go and look at how much allocation we've got, and we'll just try and cut down that allocation, and it makes big differences. Because it's true that at the point of allocation you don't pay, but later on the garbage collector has to track all of that, and it has to find the dead objects and it has to remove them, and that does cost. So these two problems are why we're like we've been groping for around in the dark for a better solution than the FP solution.
Okay. If there's one thing I've learned from the last couple of days, it's that no Scala Days presentation is complete without a little bit of theory. So before I move on to talk about our solution, I'm going to spend a few minutes to talk about the all-powerful building block that makes it possible. And that's represented here by this software superhero, Referential Transparency Man. Again, thank you to James's children for providing us the graphics. And if any of you did see the previous presentation, sorry for repeating the same joke. We're just not that funny. So I know a lot of you are familiar with this idea already, but it's so crucial that I'll just explain again. A function is referentially transparent if it returns the same result every time we call it. And it sounds simple enough, and it is. It means that when we call a function with the same input, it's guaranteed to give us the same output. Or to put it yet another way, some function x is referentially transparent if we can replace any calls to x in our code with its result and not have any observable effect on the behavior of our program. I will explain why we care about this, but first let me show you a couple of examples. So let's suppose that our function x takes some input parameter I and just computes 3 plus the log of I. This is referentially transparent. Like, that is not going to change. Given the same input, that's always guaranteed to give the same output. So let's suppose that I replace x with its result wherever I see it in foo. I won't have any observable impact on the behavior of my program because x is referentially transparent. And as I mentioned, substitutability is key to this, this idea of referential transparency. So let's take a look at a counterexample. This time, x is a call to get the current time, and foo is some function that takes an input parameter y, again another time, and it checks whether y is after x. So let's say I run this function now at 11:48 with an input parameter of y equals 12 o'clock. 12 is after 11:48, so foo returns true. But now let's suppose I try that trick again of substituting that x with a direct call to get the current time. Well, I can keep calling foo with that same input of y is 12 o'clock, and for a little while it's going to return true. But as soon as the clock hits 12, foo starts returning false, even though I'm calling it with the exact same input parameter. And that's because we're relying on this thing, this call to the local, to get the local time, which is not referentially transparent. Like any good superhero, Referential Transparency Man has some superpowers. Some of the things that referential transparency immediately gives us are order independence. We can run referentially transparent functions in any order because they're independent and they won't affect each other. And for a similar reason, we can run them in parallel. We can run them asynchronously because we're guaranteed to get the same result every time that we call them. So we can kind of schedule them when we like, and we can reorder them and run them in a way that makes sense. And one of the other things that we get is portability. So just like I can run these functions across any CPU, I can also distribute them across an entire grid of machines. And I mean, these are dummy examples, but you can imagine the benefits if it's an expensive function. And that leads on to the next thing that referential transparency gives us, which is memorization or caching. And that's going to be the focus of today's talk. So because this function is guaranteed to give the same result every time I call it, I can just cache that result, and then the next time I call the same function with the same input, I can just retrieve that result directly from the cache, because I know it won't have changed. And I get that guarantee because the function is referentially transparent. Okay, so far, maybe you're thinking that this idea of referential transparency kind of conflicts with the idea of change, and I will explain how those things get kind of tie together. But for now, this allows me to introduce the node. And this is the core construct that underpins our solution. It's an annotation, and it's a construct that we've developed ourselves using a compiler plugin, and it extends the Scala language. So when you, the developer, annotate your function as a node, you're guaranteeing to the compiler that it is referentially transparent. And so the compiler can begin to make use of well, it can transform the function in such a way that at runtime we can make use of some of those benefits that I mentioned before. So it is up to the developer to ensure that the function actually is referentially transparent. And when we first started out, we were kind of paranoid about this, as we were worried that people would do things that were not referentially transparent and try to annotate them as nodes. So we did build a tool to help check for that. But in practice, we've never used it, because it turns out that most referentially transparent functions are just kind of making calls to lots of other referentially transparent functions and then gluing together the results. Let me go back one. So what happens when we see a function annotated as a node? Well, instead of compiling this function with the conventional Scala compiler, we use Scala async, which is bundled up with the Scala compiler, and it generates a state machine representation of our function. And we explained in our previous talk why that representation was crucial for us to be able to run things asynchronously. But the main thing is that these state machines, or these nodes, feed work items into our scheduler. So at compile time, we're transforming the nodes, and then at runtime, we need something that can actually execute them. So that's where the scheduler comes in. And the scheduler can look ahead in its work queue of nodes, and it can make intelligent decisions about how to run things. And last time that we spoke about how it can batch calls to the data store, for example, or run things in parallel or asynchronously, or distribute them across the grid. But today we're going to focus on the cache. Our scheduler is cache aware, which means that before it does any computation, it looks up a result in the cache, a previously computed result. And I know that possibly some of you are thinking that after naming, cache coherence and invalidation are the hardest problems in computer science, and we're definitely not smart enough to solve that. But it's because we have the guarantees of referential transparency that our cache actually remains relatively simple. So just to reiterate, before we run any piece of code, first we look up whether we've got a result for that piece of code in the cache. But to do this lookup, obviously you need a cache key, and that's the bit that we've kind of glossed over so far. But that's where addressability comes in. And we're going to demonstrate this next bit through some live demos. So addressability allows us to address a function called with certain parameters, and then we can use that address in a cache to retrieve the result. So bear with us, because we're going to start with a very simple example, and we're going to build it up. And because we can't multitask, James is going to type loudly, and I'm going to keep explaining. So let's suppose that our function calc just multiplies together two numbers. This might be a height and a width, or a price and a quantity. Doesn't really matter. It multiplies the numbers and returns a result. And this is referentially transparent. That's always going to give us the same result. So we can annotate it as a node. And when we run it, we do what we expect. We see that print line to calculating, then the result. But now let's try running it again. The answer is the same. The difference is that we don't have that print line. Sorry if I'm blocking it. We're no longer printing calculating there. And that's because the scheduler hasn't actually executed any of the code in that body of that function. We've looked up in the cache by our function name, and we've retrieved the result directly. And we can keep doing that. I mean, James can type it again a few times. And each time we're just going to retrieve that result from the cache. And again, this is a simple example, but imagine if this was some CPU-intensive thing, or if it was making loads of calls to the data store. You want to be able to cache that result if nothing's changed. So in this instance, our cache key can simply be the function name itself. We can look up by that name and just retrieve from the cache. So let's take it one step further. And this time, calc is going to take some input parameter, which is a quantity. And it's going to, I think you need to switch slides so that we see the code.
Oh, sorry.
Yeah, it's like a
Didn't do that right,
shortcut
did I?
magic. So calc is going to take some input parameter, it's a quantity, and it's going to multiply it by this number that we now probably can presume is a price. And it does the same print line calculating. So now we call calc with some input parameter of 20, and we see the print line, and then we see the result. But let's try calling calc again with that same input parameter. And again, you'll see that we lose that print line. We just retrieve directly from the cache. So our function is still referentially transparent, because given the same input, it's guaranteed to give us the same output. And we can do this a number of times again, and we'll see that each time we just retrieve directly from the cache. And if we call this with a different input parameter, 40, then we don't have a value already in the cache. So we get a cache miss, and that's when the scheduler actually executes code, and we get a different result. But now we've got two things in the cache, the call to calc with 20 and the call to calc with 40. And so now we can retrieve both of those from the cache without doing any computation. So it's no longer enough for our cache key to just be the function name. If it were, then we could call calc with an input parameter of 20, cache that result. And if we try and look up just by the function name, we're going to get a cache hit next time, and that would just be bad. So we now need to include the input parameter as part of our cache key. And that guarantees that when we call a function with the same input parameter, we're able to address it. We're able to look it up in the cache and just retrieve that result directly. Okay, so let's build up on this some more. Now let's suppose that this function is actually a method on some class, fuel cost. And a fuel cost takes some constructor parameters, an FX rate, which we showed you before. That's just a string currency and then a rate, and a price, which is a double. And our function now depends on one of those constructor parameters. You can see it there. We're multiplying price by quantity by the rate. So let's construct a fuel cost, F. We've got an FX, James has showed you up there, that we've already constructed just to save on some typing. So we can construct this F with a constructor parameter of 30 for the price. And we can call our function calc on that instance, F, with certain input parameters. So here we're calling it with an input parameter of 20. And this is the first time that we've run this, this method on this instance of fuel cost. And so we see the print line to calculating. And now we have that result in the cache. So if we call calc again with the same input parameter on the same instance, we're going to get the same thing without printing calculating, because we're retrieving direct from the cache. So now let's try constructing another instance, G, of fuel cost, where we now change the price for our constructor parameters. And our because our calc depends on the constructor parameters, if we call calc with the same input parameter again, we have to rerun the function. So you see the print line to calculating again. And that's because this is a different instance of fuel cost. And so we need to take that into account, because our calc, although it is referentially transparent, it's only referentially transparent because we are using the same constructor parameters. So given the same input and called on the same instance of the class, this method calc is referentially transparent. And so we've annotated it as a node. And once we've run the calculation on our new instance, G, we can run it again, and we should lose that print line because we're now retrieving directly from the cache. So what does this do to our cache key? Well, if we switch back to the slides, now it's no longer enough to just have the function name and the input parameters. We also need some idea of our identity, and that's where this construct, the entity, comes in. An entity allows us to identify classes, and equality works sort of in the same way as Scala case classes and hashcode and equals defined in a similar way. So if we now have the entity identity and the function name and the parameters, then we can address calls to this function with a certain input on a certain instance of our class in the cache, and we can retrieve things directly from the cache. So we can construct loads of these fuel cost instances, and we can call calc with different parameters and we'll cache the results. So we're guaranteed not to run the same function twice, unless we've had to clear the cache, but that's another story. Right, so let's go back now to that first example that we introduced that was like a little bit complex, but really nothing on like what you'd get in the real world. But just to show you that this is like a useful thing. So this time, is this the right one?
Yeah.
Oh, we can do the tweaks. Yeah. Okay, I skipped ahead. I'll come back a bit. So we've kind of explained enough, I think, to finally get back to the problem of change. How do we apply change here? Like all of these things are vals. We're not going to be able to just mutate them. Well, we've constructed this idea of a tweak, which expresses intent to apply a change. And tweaks can be collected together and wrapped up in a scenario. And the whole scenario is this thing that we actually apply later. And once we've applied that and we're in that context, we see the changes as if we'd mutated our fields. So we've got some scenario here where our rate is 8.13. So inside the scenario, we put these tweaks. The tweaks will change the rate on our instance f to be 8.13. And now we've defined that scenario. That change is kind of neatly encapsulated into this new object, and it's a clean way to manage change. But we haven't actually applied the change, right? So to do that, we have this construct. So you see if we call calc with that input parameter of 20, we retrieve the result from the cache. That's because rate hasn't changed when we're not in the scenario. But to actually apply the change, we need something called a given block. And we can pass our scenario into this block, and then we can run our calculation in there. So if we now run f.calc with that same input parameter.
Do you want to just look at the value first?
Oh yeah, let's look at the value to prove that it's changed. So if we look at the rate in here, inside our scenario, we should see that it's 8.13. But if we are back out of our scenario, sorry James, if we're back out of the scenario, we haven't done any mutation. So this should still be 8.88, which is what it started as originally. So we're trying as hard as we can not to get away from immutable state. So now let's put this in a given block to actually apply the change, and let's do our calculation. Now, because the rate is different, we haven't done this one before, so there's no cache hit here. We're going to have to run the function. And you'll see the print line to calculating, and then a different result from last time. And if we come back out of the scenario, then we have no tweaks applied. There are no changes that we've applied, and so we have our original rate again. So this is nice. It's kind of neat. It's a neat way to encapsulate our intent to change things. But it's still probably not the code that developers want to write. And so we've added some syntax sugar on top of this that allows you to specify your tweak directly inside the given block. So given rate gets 8.13, we can run our function f.calc with that same input parameter of 20. And when we run it, what we should see is that we get a cache hit. And that's because our scenario is equal, well, the underlying mechanics are the same. When we've written the given block in this way with the tweak, we've constructed a scenario to encapsulate the tweak, and we get a cache hit because the calculation is essentially the same. And we can construct another scenario, S2, that has the same tweak in it, and we can just check that these scenarios are equal. Sorry. You're doing well so far, though. I mean, no typos that I've noticed.
Really?
Yep, good. Oh, I spoke too soon. Did you set it to a val? Yeah, okay. So we can construct our scenario, S2, with the same tweak. Yep. I mean, we've practiced this only like 17 times, so I think this is okay. Okay, good. Right? I think we're good. Right, and now we can check that it's equal to our S that we had before. It is, which is cool. So that means that under the same scenario, we're going to get cache hits. But what this means is that we need to update our cache key. So let's go back to the slides again and see what this does. So now it's no longer enough just to have our instance and our function and our input parameters. We also need the scenario under which we're running the calculation in order to be able to address our calls to the function and to apply change. And so we include the scenario as part of our cache key. So the first time we called calc with an empty scenario, which means no tweaks. It means that rate is 8.88, which is how we constructed our object in the first place. But we have another scenario where we've set the rate to 8.13. And that's what allows us to cache that call to calc under any other scenario. Okay, so now that we've covered that bit, and now that we've shown you change, we can show it, we can go back to our original example, the more complicated problem. So, if we get the shortcuts right, modify, yep. Okay, so this time we have a, whoa, you want to go back to that grapple?
Hold.
You're in a new one. Use the mouse. I mean, it's okay. People won't know.
No, I'm lost though. Where's the thing?
There.
But why can't I? Hold on. There we go.
All right, but we still need to be in this one.
Oh, okay.
All right, sorry about that. Live demos. Okay, so this time we have a flight that we've already constructed because it's kind of long. But the flight has a fuel cost, which we were using before, and it also has this occupancy score, which is another object that contains a rate and some like occupancy of the flight. So we can call these functions, we have two functions that we've defined on flight, and those are fuel cost, which uses the fuel cost object to calculate the rate. And we've also got projected occupancy, which uses that occupancy score object to calculate some projected occupancy. So we don't have to understand this entire dependency graph in order to make a change. The platform can kind of propagate changes through the system and only tweak the things that need to be tweaked. So let's say that we now change the flight.fuel.local currency, whatever it is that we need to do to change the rate. And we can tweak it to be something else. And then calculate the fuel cost. Yeah, fuel cost. And our system propagates that change through so that we don't have to kind of bend the dependency graph into shape or understand it at all. And we can do the same thing again with projected occupancy. Where if we change the rate, then that should have an impact on the occupancy score as well. So what we've done, we think, is to come as close as possible to that syntactically nice way of just mutating vars in a procedural language, but without losing the benefits of immutable state, and also without incurring the costs of, firstly, difficult to read code, and secondly, creating new objects all the time when we're trying to apply a change. So this way our developers get to write the code that they want to write. They get to just set rate to 8.13. And our platform can still maintain the benefits of referential transparency because we take into account the scenario and the instance identity and function and the parameters in our cache key.
Okie doke. Yeah, so to summarize this whole thing, you saw that in the end we were able to create those 5 objects and we were able to locate that currency rate and change it, and when we did, it was effective for everything. But there are a few things that are different to the other models. Like we've got the syntax of the OO model, but we're only creating one object for each change. So like our change is linear, like our impact of object creation is linear to the change that we're trying to make. Rather than having to reconstruct the whole object graph, which is what we would be forced to do in the FP model. Also, I think it's easier to read the code. When you read the code, which has this thing where I've said, I'm going to change this one thing here, it's much easier to understand that that's what you're trying to change. And the runtime takes care of doing those things efficiently, and that all bound together. That means that we've taken advantage of the fact that because you can address the thing, And all of that comes from functional programming. Like the addressability is only really possible because you need that to gain the benefits of referential transparency. Because once you've got the referential transparency, obviously the next step is to cache things. But if you cache things, then you make them addressable, right? So now we've got the addressability, you can also use that address to make a change. And that's really the solution that we've settled on, and that's what we're here to talk about. And you know, maybe Gjeta mentioned that in another talk we talked about concurrency. We can also use this change mechanism to still get the benefits of being able to parallelize all of the execution, which is obviously also beneficial because you don't wind up with all these problems of multi-threading that you tend to get with change, because the change is bound up inside of this scenario and it's easy to understand. So just a little bit more. We've got a few more minutes, I hope. Did we make it?
I think
we've got a few more minutes. So we've added this as a kind of additional thing, 'cause in our run through we had time, which is about like how addressability can help you elsewhere. So we have this addressable code, but also a UI is addressable, right? You know, if you've got your UI, you've got the window, and in this case, inside of the window, I've got a grid, and inside of the grid, I've got various widgets, a label, and a text box. Like that's all an addressable thing that I've got there. And as we've spent the last sort of half an hour explaining, our code's addressable too. So we've got these things, and we can reach inside, and we can address the code. Now, the nice thing that we've got is that we can talk to this scheduler runtime that we have, and we can ask the scheduler runtime to operate in a completely different fashion. So we can say, okay, we want you to start running, and when you run, and we have a DSL that looks like this, we want you to connect two sides of addressable componentry together. So we have these operators that we added, and now this text box here can address the rate. And then the fuel cost is basically another address where we're reading the rate out. And we get this UI up the top here, where the runtime knows that when a change is made to the text box, it will like create a tweak. And then it will push the tweak into the runtime, and the runtime will work out what needs to be recalculated. Now it knows what needs to be recalculated because the first time when it read that addressable flight.fuel cost, it will have worked out, well, that flight.fuel cost, that touched this rate. So I know that if you change that rate, I need to rerun it. So by having this hydrated model where I can see my dependencies, and by having this addressability, I can write code like this, which builds UIs, and hopefully Gjeta is about to actually show.
Yeah. So
it's not fiction.
this is kind of tiny. Let me do the thing. Is that better? Right.
Can you guys see that?
Yep.
Hey, and the numbers match. Which we always have thought they were going to. That's all fine. So we can build UIs in this style, but we don't. You know, this is a demo, and hopefully it ties back and it makes sense how we use that addressability in order to achieve this like very simple and nice way to build reactive UIs. But we also have got much bigger UIs which have got more complexity. It still works and it scales because, you know, at any time you're only holding on to a bunch of objects which represent the changes that you wanted to make to the underlying set of objects that you created. And that means that you can scale and do like actually quite significantly complicated things with these UIs. This just demonstrates like we've got a 3D thing here where you can add like noise and twist it and stuff, and when you click on points, it knows that you've clicked on the point and it can represent the point in the container and stuff like that. Okay, so how do we do this? I think there's a kind of a balance. We have extremely demanding people who are like, well, I don't want to write code that looks like that. It's hard. But at the same time, the people who sponsor us internally have backed us up extremely well with resources and helped us to be more effective. And I think that's why we got there. And also, you know, we're two people of a very large team of 500, and there are some spectacularly talented developers and engineers in that group. And we're just here to represent the work that they have all collectively done to achieve this. It definitely is no one person's brainchild. It's the result of many different people working together to build these ideas and make them a success. we still have loads of stuff to do. We want to improve the way that we do this reuse. You know, we've shown you some primitive things here, but actually there are much more complex ways that we can do reuse. We also have various ways where we know we can improve performance by taking shortcuts because of information that we have available because of the model. We want to do better with like our programmer experience, which at the moment is slightly open, and it needs to be more possible for people to control, like what can be changed, which we use obviously under advisory, what can appear to change. And then we have like a whole bunch of other things where we have problems like dealing with the JVM. It gets confused by the fact that we just allocate caches, which we don't care if we lose them, because you know, if you lose something that's referentially transparent, it's not a big deal, you can just create it again. So there are lots of things that we still want to build. And we haven't got time today, but we've got some nice tools which enable you to debug, but we want to improve those as well. So there's a lot to do, but it's been a great project, and I think that these ideas are worth sharing, which is why we're here today. And that's it. If anyone's got any questions for Gjeta or I.
Okay, thank you very much,
Thank you.
Gjeta and James. We have some time for some short questions.
We went over.
Put that down without touching it.
Okay, so thanks for the great presentation. One question I had is what you showed where you had an object graph which was fixed, and then you applied tweaks to the attributes of some of the nodes of the graph. Can you also tweak the graph itself, that you essentially change the edges in the graph?
Yes, that's the short answer. Yes, I mean those fields we just tweak primitives because it's quicker to type in the demo. Right. But you can tweak in another pointer. And that works. And that works as well.
And then my second question was: so you started with a base model with the initial values of everything, and then you applied tweaks. Does it even make sense, or do you do that at some point you can consolidate a tweak in the base model and thereby have a new model to start with? Because I imagine a lot of changes will accumulate over time.
Yeah, but also. We didn't really go into the details, like, because we've got this compiler plugin, and when you write at entity, it kind of wakes up the compiler plugin and we change everything. There are lots of other things we can do, like where we have one of those nodes, what we've also got is a hidden field. So if you change it, we'll stuff the new value in the hidden field. So we kind of effectively are doing that anyway. So I mean, the answer is yes, kind of, but never conceptually. Like conceptually, the developer always lives with the model where, you know, they've got their change which they've applied, and they've applied it, either they've given the given block or they've created this runtime which is reactive, and they've got that. So we can do it physically, but never logically. We would always stick to the model, because then it's kind of like the principle of least surprise for the dev. Yeah. They just get the model they expect.
Okay, thanks.
There were some more questions.
At the front.
There's a few down here.
You showed that you changed the rate and the FX rate, and this affects the caching. What happens when you change the currency name, which is not used in the actual computation? Would this affect the cache, and does it have anything to do with the fact that the rate was marked as a node, as the only field in the entity that I noticed is marked?
Yeah, we forgot to say that. Yeah, you can only change things that are marked as such. So because it's only then when we have the interception, and essentially we have different styles of cache matching. So the most primitive, it would just be, well, you changed something, so therefore everything is invalid. But we have more sophisticated models where we can be like, well, you changed that, but we know you don't depend on that, so therefore you know, we'll just use the cache value. So the answer is it depends, but we are aware of that issue.
It is configurable. So if you know that a calculation is expensive and you want a cache hit as much as possible, you can change your configuration so that we do that slightly more expensive check when we look up to make sure that even if some of the tweaks don't match, we still don't depend on that in our calculation, so we can get the cache hit.
So you have mentioned that you did this to gain performance, to avoid the drawbacks of copying. Do you have any hard data about that?
It's hard to like rebuild an existing system, and with like in the FP model and in the not FP model. But what we have done is where we've decommissioned systems, which we have done some analysis about how much most of that analysis actually focused on how much of the code was necessary to do the change, or like how hard it was for the programmer. But in terms of runtime, we have done some analysis on that, but we've never decommissioned an FP system of any like significant size. So I don't think we could realistically claim, it's this versus that. But I think that, even in the small example, even if you count the enclosing objects, because we're big O n, right? But we still create 2 enclosing objects. We've got the tweak sequence and the scenario. Even if you count them, we still are creating less objects to achieve the same change. And the bigger the object graph and the more complex it gets, the more you're gonna save. We don't know what the number is, because reasonably people who write in FP as well will change the object model so that they get a linearization and so that they minimize the amount of changes. So it's not an easy thing to make, but I think that it would be pretty hard to argue that we're not saving. It's just we just don't know by how much precisely.
Any more question, or one last short question?
There's one here.
Can you use the mic? Sorry. Thanks.
Have you tried disabling the cache, and what's your cache hit ratio?
So, I mean, we've given like a very stylized view. You can disable the cache and then stuff runs real slow.
But I mean, there is overhead to switching on caching, so you wouldn't do it to multiply together 2 numbers, for example. So there's a lot of machinery there. But for an expensive function, yes, it would be slower.
But also the cache hit ratio varies. But what we have is we've got tools, so you can like run the app and see what your cache characteristic is, and then reconfigure the app so that you get the optimal like caching behavior for the app that you're running.
Okay, I think we have to turn to the next talk then, and maybe you can answer questions later on.
Yeah, we'll be around if you want to ask us anything. We're here, so just come and find us.
Okay, thank you again.
Thanks.